Second talk is the embedding quantum program verification into Dafny, and by the Henry Allard from the Iowa State University. Yeah.
Thank you for the introduction. Good afternoon, esteemed faculty and staff, faculty and students of OOPSLA 2025. I'm Henry Allard. I will be presenting our work on embedding quantum program verification into Dafny. This is a joint work combined with Feifei Cheng, Sushen Vangeepuram, Seyed, Jafari, Alex Potanin, and Liyi. So how many here are familiar with quantum computing? Okay, I'm seeing some hands. That's good, that's good. Some of this will be review, unfortunately, but why quantum computing and why verification? You've probably seen in the news plenty of articles ranging from informative to sensationalist, but quantum computing is focused in the industry because of its impact, or its potential impact for substantially faster algorithms. They'll unlock orders of magnitude and speedups for complex problems such as cryptography, gene folding, and data processing. Some of these example algorithms include Shor's algorithm, which is for factoring large numbers in polynomial time. This is maybe the most famous quantum algorithm. Grover's algorithm that deals with unstructured search in a sublinear time, O of square root of n. There are also algorithms for simulating physical systems and solving linear equations. But how are these algorithms constructed? Currently, we use the gate model of qubits and circuits to construct quantum gates. So a single qubit can have infinite states, and qubits can also become entangled. This is where a lot of the complexity arises when dealing with quantum systems. So constructing algorithms with qubits in entanglement and qubits in multiple states can be very difficult, time-consuming, error-prone. Most of this work is done by physicists and doctorates. A question of our team was, how can we make this easy for regular computer programmers? So writing out the state semantics of each qubit is difficult. How can we reasonably encapsulate this in a program semantics? Not everyone has a quantum computer, so how can we allow developers to write code and verify that the results are correct on their own physical classical computers? And also, how can we design this language to develop more use cases for quantum algorithms? Our answer to that was QafnyC and QafnyC. Previously, we introduced QafnyC, which was a theoretical language for quantum computation. However, now we've implemented QafnyC in QafnyC. This is a proof system capable of automatically verifying quantum programs, and it compiles directly down to Dafny. QafnyC is based on Hoare logic, so terms like pre and post condition, loop invariance, and the QafnyC triple should be familiar here. And we can use SQIR to compile QafnyC down to OpenQ assembly. So before we talk about exactly what QafnyC is, I'm going to do a little rundown of quantum computing. In the classical world, we have a bit, which is a 0 or a 1. However, in the quantum world, we can have more of a gradient between the two. To notate this, we use vector notation, alpha and beta. Alpha and beta are both probability amplitudes. Alpha squared is the probability that the qubit will measure 0. Beta squared is the probability that the qubit measures a 1. Likewise, the sum of the squares must equal 1. We can extend that by saying vector 1, 0, therefore 0. We call this ket 0. Vector 0, 1 is 1. We call this ket 1. But then we can get more complicated, longer qubit strings. Vector 0, 1, 0, 0 would be a classical 0, 1 or a ket 0, 1. However, in quantum, I mentioned entanglement before. We can combine these kets with amplitudes to create new states. For example, the ket plus, which is the probability of measuring a 0 or a 1. We can also prepare these states in entanglement. This is an example of a Bell state preparation, where we apply Hadamard on the first qubit, control NOT gate onto the second, the final product of which is 0, 0 or 1, 1, not 0, 1, not 1, 0. If we measure a 0 from the first qubit, a 0 must result in the second. If we measure a 1 from the first qubit, a 1 must result in the second. So what have we introduced in QafnyC? In QafnyC, we have a new automated verification system. We can use types to direct our analysis and verification, and we've introduced two new types, or we've modified the EN type and introduced the amplitude amplification, or AA type. We've also extended the condition semantics to cover a greater range of programs and algorithms. This includes adding 37 verified quantum programs, and some critical developer features such as debugging support and feedback when Dafny fails. So as an example of QafnyC code, this is a very simple example of the bell pair state. We have an 11-line method here. We have a precondition requiring that the input to the program is cat 0, or is to cat 0. We have a Hadamard gate application, then a controlled NOT, working from the first qubit onto the second, flipping the bit, and then finally ensuring the precondition is 0, 0, or 1, 1, equally likely. This is the Dafny code. It compiles down to, I don't expect you to memorize all of this, it's almost 220 lines. So as our design for QafnyC, we've abstracted quantum circuits into C-like programs. This is evidence very similar to Dafny code. We can also verify pre- and post conditions of the quantum circuits, and we can simplify the specification of quantum semantics. And finally, we automatically verify those QafnyC programs in Dafny. So what does automated verification look like? So QafnyC will automatically convert QafnyC code into Dafny, adding the required pre- and post conditions based off of the shorter semantics we use in QafnyC programs. For example, to specify, again, that bell state, we can use this very simple line of QafnyC code, an entangled type, two possibilities, both amplitudes 1 over square root 2, 0, 0, or 1, 1. This QafnyC will take this and then convert it into a few lines of Dafny, here checking the amplitudes and the basic hets at the end of the program, at program end. And what does type-guided automation mean? In QafnyC, in the second paper, we've introduced AA types and EN types with a parameter. We can generate constraints based off these types, and the type complexity drives Dafny code complexity. So we have 4 quantum types: NOR, HAD, AA, or amplitude amplification, and EN with an N parameter. The NOR type represents any basic ket, 0, ket 1, ket 1, 0, 1, 1, 1. It's represented in Dafny with real and a sequence of bit vector 1s. This is simpler compared to the other types. Hadamard type represents any singularly superpositioned qubit, so ket plus, or maybe 2 ket pluses. Amplitude, it is converted to the Dafny type of amplitude real and a sequence of reals. Amplitude amplification is used for a specific group of problems that I will get into later. All that you need to know now is that it basically partitions the qubit string into 2 separate groups. This can be represented as 2 sequences of length 2, a sequence of reals, and a sequence of bit vector 1s. And then finally, EN type. This can represent any qubit string. An example value is this GHZ state. Essentially, think bell pair, but for more qubits. The n decides the number of sequences, so it's an n-dimensional sequence of reals for the amplitude and an n plus one dimensional sequence of bit vector 1s for the basic kets. What is amplitude amplification? An easy example of this is Grover's, where we're splitting basic kets into a good and a bad group. Essentially, amplitude amplification problems work by increasing the probability of measuring from the goods group and decreasing the probability of measuring from the bad group over time. This requires constant or multiple applications of the quantum circuit. An example of what the semantics look like, this comes directly from the original paper, Amplitude Amplification and Counting. This is what amplitude amplification problems essentially look like in practice. This graphic shows kind of how successive rotations around a state vector collapse the state closer to the target vector. So to help with these problems, we've introduced the amplitude amplification type. It separates the 2 groups with different amplitudes by a function that returns true for the good group, false for the bad. This is a very simple example from the Grovers. We can see we're partitioning the basic kets into ones where the geometric sum of the amplitudes is sine v when f returns true, and where the geometric sum of the amplitudes is cosine v when f returns false. So in QafnyC, we also have over 37 verified programs, including Grover's, Shor's, Simon's, and amplitude estimation. As an example of how complex these programs get in Dafny, Bell-Pair, again, turns into 220 lines. Grover's, which is 23 QafnyC lines, turns into 230 Dafny lines. We've also introduced some useful features, such as two-line feedback, converting the Dafny error codes into QafnyC ones. This is really useful for larger files, such as amplitude estimation, which has over 100 lines. So we can convert directly from Dafny back into QafnyC. Our findings are that QafnyC can quickly verify algorithms with fewer lines of code and better feedback to the programmer. We have these are the 37 programs that I've been mentioning throughout this talk. As we can see, they're ranging to maybe a maximum of 50 lines of code, whereas compared to CockQ, QBreaks, and SQIR, even something like GHZ can get to 119 lines of code. So it's a lot easier to write code or write quantum programs and then verify them using QafnyC. In the future, we hope to use symbolic execution to generate pre and post conditions, add additional features, additional language semantics, and cover a wider variety of programs, and then use this in some real-world research papers, maybe create some new algorithms, and publish the QafnyC code associated. Thank you very much for listening. I now welcome any questions with the remainder of my time.
Do you have any questions?
Hi. So you're mentioning you're verifying Grover's algorithm. I have two questions. So for one, you have this target oracle that you're optimizing for in the Grover iteration, right? This function that you want to satisfy. What function are you using for that? And did you notice that, like, when you use more complex target functions, that like the solvers struggle, or does it actually scale?
That's a great question. Essentially, we accept in a function, like I believe it's a natural that returns a Boolean, and we can base it off of that. We don't, in the actual proof, we don't define that function. So we leave it up for Dafny to figure that out. So I hope that answers the second question as well. We don't make it complicated, so it doesn't. We can't really compare different functions. But thank you for the questions.
Hi, thank you for the nice talk. So from the kind of small snippet that I was able to memorize of the slide that you flashed,
oh no,
I saw that there's like a lot of quantifiers and complex features and so on.
Yes.
Did you struggle with Dafny performance, or did you employ some tricks to get it to go through the proof?
Yes, actually, our paper mentions more on that. But a key insight was using sequences that are immutable in Dafny over, I believe, arrays, just because it was faster. So some of the longer ones did take like up to a minute. Some of them took a while to massage into verification.
Okay.
I hope that answers your question. Thank you.
Yeah, thanks. Yeah, a minute is nice.
Very nice talk. Could you say a bit more about what is the property you verify for Shor's algorithm?
For Shor's algorithm. The end state of the qubits. I'm not sure I understand the question. I'm sorry.
So it's very complicated to state the correctness property for Shor's algorithm because the algorithm is probabilistic.
Yeah.
So I'm wondering what your correctness statement is.
I'll take a look at that and I'll get back to you. Thank you.